Have you ever asked an AI a question, a simple math question, and got an answer that was delivered with total confidence, but was also completely and utterly wrong? Yeah, it's a huge problem. But what if the issue isn't just some random bug? What if it's baked into the very foundation of how AI thinks? And what if we could replace its talent for guessing with an ironclad ability to prove?
Right here. This one word is really the heart of the problem with even our most powerful AIs today. Probabilistic. No matter how brilliant they seem, deep down, they're just playing a game of odds, predicting the next most likely word in a sentence. It's an incredibly sophisticated game for sure, but it's still a game of chance.
And this slide really lays out the two sides of the coin. On one hand, you've got current AI playing that high-stakes guessing game. But on the other, there's this totally different approach called Deterministic Latent Logic Solvers, or DLLS. Instead of guessing, DLLS treats a problem like a physics simulation that just has to settle into one single logically consistent answer. It's not about what's probable, it's all about what is provable.
So here's what we're going to cover. We'll start with AI's guessing game, then dive into this new physics of truth. We'll see how it actually reasons on a kind of digital canvas, and then get into why this deterministic method just wins out. And, maybe most importantly, we'll ask if this could be a cheaper, more reliable way to build AI and what that means for the future.
Okay, first up, AI's guessing game. I'm sure you've heard the term hallucinations, right? That's when an AI just confidently makes stuff up. And it happens because it's fundamentally designed to sound plausible, not necessarily to be factually correct.
This right here gets to the core of it. When a large language model tries to solve a math problem, it isn't actually doing math. It's just mimicking the patterns of what a math solution looks like. It has no real concept of closure, which is a fancy way of saying it doesn't understand that if you know one fact, other facts must logically follow from it. This makes its reasoning brittle and, honestly, a nightmare to try and debug.
So let's pivot to the solution, a new physics of truth. The idea here is, instead of trying to teach an AI to copy how humans reason, what if we could turn a logic problem into a physical system and just let the laws of physics find the right answer for us?
Think of it like this. Imagine you have a stretched-out rubber sheet. A logically wrong answer is like a marble sitting high up on that sheet. It's an unstable, high-energy state. The DLL's model learns to apply a force, a field, that pushes that marble downhill until it settles into the deepest valley. That lowest energy valley is the one and only correct, logically sound solution.
And this is the absolute game changer. An LLM is always asking, okay, what's the next word I should probably write? But a DLS takes a step back. It sees the entire problem, all its parts, and all its logical consequences, all at the same time. It's a totally holistic view, not a sequential guessing game.
So, how does this actually work? I mean, how do you take a whole math problem and turn it into a single object? Well, the answer is you put it on a canvas, a fixed-size canvas.
Get this. Every single algebra problem, it doesn't matter how simple or complex, gets mapped onto this exact same data structure. It's a grid with 6 layers, each one 256 by 256. It's like a standardized container for pure logic. And because its size never, ever changes, the whole process becomes incredibly predictable and super efficient for hardware like GPUs.
And each of those 6 channels, or layers, holds a specific piece of the puzzle. You've got layers for the symbols, the numbers themselves, and other meta-information, like is this part of the original problem or is it part of the final answer? It's just a super organized way to lay out an entire logical system on one single board.
So here's the entire workflow from start to finish. Step 1, the problem gets encoded onto that canvas. Step 2, the system evolves, that's the physics simulation part, until it settles into its most logical state. Step 3, that final stable grid gets decoded back into math we can actually read. And then, and only then, that perfect logical trace can be handed off to a regular LLM just to translate the steps into plain English. The heavy lifting, the actual reasoning, is all deterministic. The LLM is just the spokesperson.
Okay, so why is this approach so much better? Well, it all boils down to 2 things: reliability and pure, unadulterated efficiency.
And this table really drives home a massive advantage, the computational cost. For an LLM, the cost goes up with every single word it generates. A longer, more complex answer is always more expensive to produce. But with DLS, the cost is fixed. It's always the same. Why? Because the canvas size never changes.
It just takes a set number of steps to solve the problem, which makes it faster, way more predictable, and a perfect match for modern GPUs. So the bottom line is this: you trade in those frustrating hallucinations for clear, obvious errors. If the system fails, you know exactly why and where it failed. The entire path to the solution is traceable, almost like you're debugging code. And it does all of this using math that's tailor-made for the hardware we already have.
Now, let's talk about something that might be an even bigger deal: the insane cost of actually building these models in the first place.
This is literally the billion-dollar question in AI right now. Training these giant foundational models costs a fortune. But this DLS approach, it might offer a radically different and cheaper path forward. Just look at the difference in the training data. It's night and day. LLMs have to learn by scraping the entire messy, chaotic, error-filled internet. They sift through trillions of data points hoping to find patterns. A DLS, on the other hand, can be trained on perfect, clean, synthetically generated data, basically a pristine library of absolute mathematical truths. It learns the fundamental rules from a perfect system, not just patterns from a messy one.
And here's the incredible implication of that. When your training data is that clean, that structured, and that targeted, you just don't need as much of it. The cost to build a foundational model for logic and math could be orders of magnitude lower than what it takes to build a general-purpose LLM. This could completely change the game, democratizing who can build powerful, reliable AI.
So finally, let's just zoom out for a second. What does all of this really mean for where AI is headed?
The ultimate promise here is a fundamental shift in what we should even expect from our AI. We could finally move from models that are just plausibly correct to models that are provably correct. And for fields like science, engineering, and medicine, places where a mistake can have serious real-world consequences, this isn't just an upgrade, it's a full-blown revolution.
So I'll just leave you with this final thought. For the past decade, we've been building AIs that are masters of probability. What happens when we start building AIs that are masters of certainty? What new frontiers could we conquer if correctness was a physical guarantee and not just a roll of the dice?